Hello Math 7 students, this is Utah Middle School Math Project 1.1b, Probability, the Race to the Top. This is part 2 and this will finish the lesson. To review, we did the horse races in our last class where we rolled two dice, a pair of dice, to see what number, when they are summed together, what number when added together occurs the most. And we ended up making a couple of probability models. So instead of just testing it out in our experimental probability, we actually are trying to determine the theoretical probability, which required making a couple of different models for how all the different ways that we can have different rolls of the dice and what they will add to. In both of these versions of the probability models, we saw that there are 36 total possibilities when we are rolling a pair of dice. And so we were trying to find the probabilities of each one of the sums, and I need your help with that now. 3, it looks like we can roll a 3 out of 36 times, yes? Okay. In a second, I'm going to ask you guys for these as percentages. Right now, just help me confirm these fractional totals. 3/36 does, however, simplify to 1/12. Yes, Joshua? Thank you. I was looking ahead to 4. You are right. I appreciate that. 2/36, because it happens right here. 2 and a 1 or a 1 and a 2. Only 2 possibilities. 2/36 simplifies to 1/18. 4, as I just incorrectly mentioned for 3, 4 has 3 possibilities, 3, 1, 2, 2, and 1, 3, so that one is 3 out of 36, or 1/12. 5 is at 4 out of 36, 4 out of 36, which simplifies to 1/9. 7 ends up being 1, 2, 3, 4, 5, 6. Is this correct? Did I make a mistake here? I did make a mistake here yesterday. And you guys let me finish yesterday's recording and publish it to YouTube with that mistake. Thanks. Thanks a lot. So the 6 was 5 out of 36? Okay. And the 7 is 6 out of 36, right? Okay. All is fixed now. 6 out of 36, which is 1/6. 5/36 doesn't simplify. 8. How many ways can we roll an 8? 1, 2, 3, 4, 5 36th again. All the ways that we can roll a 9. 1, 2, 3, 4 36ths. Or 1/9. 10, we can roll a 10 in 1, 2, 3 different ways. 3/36 or 1/12. And 11, 2 out of 36 or 1/18. And 12, there is just 1/36. Only one way out of 36. Now, with that being said, I definitely need your help finding these percentages. Pause the recording until you make sure you have that done as well. I'm going to pause the recording and they're just going to appear on here so you don't have to wait through that. Pause the recording now. All right, here is our theoretical probability for each one. Let's see how it compares to what you as a group got or what I got. All right, now these, we just calculated decimals, not percents, but let's compare, understanding that this given as a decimal and this given as a percent. Probability of a 2, this is the theoretical probability. How does it compare to my own experimental probability? Is it exact? No. Is it pretty close to what I should have gotten in theory? Yeah. This next one is kind of interesting. 3 out of 30 versus 2 out of 36. So this was actually a 10%. How does that compare to the 5.5%? A little bit higher, right? Is it still relatively close though? Yeah. This one, how does this compare to the theoretical probability? Pretty close. Again, are any of these going to be perfectly accurate? Probably not, but are they fairly close? Yeah, in fact, I think that in all of it, there's really only one that ends up matching. The 7 is a 16.6% in theory, and I actually got it 16.6% of the time. So that's kind of interesting. I don't know how many of the others match perfectly. I don't think any of the others did. But that's one of the things that you need to make sure that you understand is, although we can calculate the theoretical probability, and the theoretical probability is great for making predictions. Is it ever going to perfectly match what actually happens in reality? There's always going to be something else that's going on. So that's one of the things to take away from all of this. The other thing is I want us to really have a good solid understanding on what are some possible options for the probabilities. To really truly make sense of that, I want you to add up all of the fractions, find the total, add up all of the percents, what is the total? We should, in theory, get the same answer, but I want you to take a second, add up all of the fractions, add up all of the percents. Again, here's all of these fractions. We all got the same fractions, so take a second, add those up. You do have calculators, but also we have a common denominator. That's why I didn't simplify, or I wrote them simplified, but also unsimplified. What do the fractions all add up to be, and then what will all the percents add up to be? We're going to pause the recording as students calculate that and figure that out. Okay, when I add up all of these fractions here on the top row, what did we end up getting when we add up all those fractions? Dylan, 1 whole, 36 out of 36, or we get a perfect 1 whole. What happens when we add up the percents? I'm curious to hear your responses here because lots of different things could have happened. Sophie, you got 100%. How did you get 100%? What did you add? So what I'm really asking is when it was 2.7 repeating, how did you add that? Okay, so you did 2.77 here. So on each one of these, you gave yourself 2 decimals? Perfect. Okay. Is there anybody who gave yourself just 1 decimal when adding? And Grant, when you did that, what did you get when you gave yourself just 1 decimal? Yeah, 99.4. Sophie, it sounds like if you gave 2 decimals, then you would have gotten the full 100%. Okay. Joshua. Okay, so you use the exact full decimal by using the copy paste feature. Okay, a lot of work, but what did you end up getting? A full 100%, I'm guessing. Okay, what if we had rounded these? So instead of 2.7 over bar percent, what if I called it 3%? And here instead of 5.5%, what if I called it 6%? 8.3% would round to 8%. Am I going to get 100% when I add them up this way? No. In fact, if I add up these numbers, giving myself only 0 decimal places in that percent, we end up adding up to 101%. So which is better when we are dealing with probabilities? Which is better, percents for probabilities or fractions for probabilities? Discuss at your table. What do you think is better? Yeah, I heard clear across the room, I heard fractions. Fractions are going to be better. And I agree for the most part, yes. I think that fractions, number one, I've been saying all year, fractions are friends, right? So we should be able to read a fraction and know what it means. But we're not going to have those same sort of rounding inconsistencies and issues when we are dealing with those fractions. So I like those fractions better, but also having an understanding or an approximation of what it could be as a percent. Even when I think about 1/36, if I'm thinking about it being approximately 3%, that can also help my brain understand just how very unlikely rolling a 2 or a 12 is. So add up all the fractions, what do we get? We got 1, and it depends on how you actually thought of those percents. You could have gone anywhere from 99.4% to 101%, and we understand why we're seeing that difference. So now it's time to really think about how we can make this bigger. Suppose there are 200 races. That's 200 rolls of the dice. We stopped at 30 races. So if there's 200 races, use your experiment, use your theory. How often do you think that number 7 horse would win? Show all of your work and explain all of your reasoning. Once you do that, if you're waiting for me to continue, we have 12A and 12B and 12C that we can also begin answering. So 200 races, how often do you think horse number 7 would win? Pause the recording as you work with your groups to calculate that. Ready, set, go. All right, there's 200 races. How often is horse number 7 going to win? What do you think? And tell me how you're getting there. We'll start with Davin. How'd you get 33? Okay. 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 Very nice. Okay. So you're saying this is already a percent. 16.6% is 16.6 per 100. Let's use equivalent ratios. We're going to change that to a 200. So instead of 100, that's going to be 200. So we're using those equivalent ratios. We're just doubling it. And what is 16.6 times 33? Don't you really get like, yeah. And you just decided, well, that 33.3, we can't win a third of a time or 3/10 of a time or whatever. I think that's supposed to be repeating. So you're saying, well, that's about 33 times. Good. Any other strategies? Yes, Joshua. Okay. I think that this is all so funny that you guys are saying this. Because didn't we just discuss which one is better? The fractions. And both of those students who shared, one used a percent and one used a decimal. What would be better and give us the most precise answer? Because can we really type in that 0.6 repeating enough times to truly show that it's repeating? Not really. So what is one way that we could do it is just using that fraction 6/36, right? Or 1/6. And then yes, you're just taking that 1/6 and you're multiplying it by 200. Yes, Joshua? That is a lot more work because you have to click up too many times in order to actually get there. By the time you click up that many times, you also could have just typed it in. You're spoiled and you have good calculators that let you do that. Not all students who might be watching this video will have that opportunity, especially if they are watching it at home. So who's always right? Mrs. Proctor is always right. There you go. 1/6 times 200. Either way, you get 33 times. Would it be appropriate to maybe say 34 times? If this 33.3 is repeating, is it better to round down or to round up? Why down? Why down, Oren? Okay. What if we were dealing with people? 33.3 people. Are you going to say that this 0.3 of a people doesn't matter? Or would you round up to 34 people to account for the fact that it's a partial person? I would round up. So, one thing that I want to address in this, can I please have your attention? Mathematically speaking, abstractly speaking, does it make sense to use that 3 and round it down to a 33? Yes. When we start talking about quantitative, if you're going to win 33 and a third of a time, do you think that that is appropriate to round it up to a 34 so that we're not discounting that extra little possibility there? So I think it's appropriate to say 33 or 34 times. I want you to also think abstractly. Yes, abstractly we would round down to 33, but quantitatively sometimes it makes sense to go up. Oren? What do you mean, wouldn't the 33 be a percent? Yep, look what we did. 16.6% is 16.6 out of 100 times. But we're not doing it 100 times, we're doing it 200 times. So think about where this percent even came from. This was 3 out of 36, which is equal to that 16.6%, right? But 16.6%, we can rewrite it back as a fraction. Instead of this fraction, we can write it as a fraction out of 100, which makes our job a lot easier. How does that 100 change to a 200? This is assuming that instead of 36 horse races, instead of 36 times this happening, we would have raced 100 times. And if we would have raced 100 times, we would have rolled a 7 16.6 times. But we're not doing it 100 times, we're doing it 200 times, so we're doubling that. Does that clarify the relationship between those numbers? Okay, so again, we have an idea, we have some strategies that are going to work here, but let's go with math practice 6. Let's be a little bit more precise and remember that fractions are friends. So instead of using the percentage and using the decimal, let's use the fraction because fractions are friends. Let's continue to predict, what if we raced 500 times? What if we raced 1,000 times? But please note what's being asked. 12A is horse number 7, 12B is horse number 2, and then horse number 12. And then we have other questions down here. So use those same strategies that we talked about before, but here is my encouragement. Will you please remember that fractions are friends? Let's go for a level of precision since we are dealing with some quite large numbers, 500 races and 1,000 races. Pausing the recording again as students work on this. Ready, set, go. Okay, A, since I still want to know how many times horse number 7 will win, I remember that horse number 7 will win 3. You guys did this to me again. You let me go on. It's not 3 out of 36. It was 6 out of 36, right? Come on, guys. So we know that horse number 7 wins. I did it again. Not 3 out of 36. 6 out of 36 times, which is the fraction 1/6. So using that fraction 1/6, I probably would have multiplied 1/6 by 500. And when I multiply that by 500, what do I get? About how many times will horse number 7 win? Liv. 83 times. How'd you get that? Like what, when you typed in 1/6 times 500, what did you actually get in your calculator? Okay. Okay. Would it be appropriate to round up to an 84 here? We talked about this in the last example. You're going to just completely discount this extra time? Could we round up to an 84? Yes, guys, quantitatively speaking, it makes sense to round up to an 84. You have to understand the difference between math, abstract thinking, and quantitative thinking. Once again, if we said that the population of Tooele is 83.3, and you're going to just say, that doesn't matter. Yeah, that is unfair to that partial person. It makes more sense when we're dealing with quantitative to take that extra part after the decimal that feels like it doesn't make sense, and sometimes it does make sense to round up. So, is it wrong if you say 83 times? No. But I think it's worth noting that it is appropriate to say 83 or 84 times, knowing that that 0.3 does have an impact on that probability. Okay, with that in mind, 1,000 times then. 1,000 times, we're going to repeat that process. We have 1/6 times 500, which is about, or I guess equal to in this case, because I want precision here, Joshua. Good job. You caught it. What is the probability of number 2, horse number 2? Is it the same as horse number 7? No. So you should not have taken that 1/6. Sometimes I make mistakes on accident, like the 3/36. Sometimes I do them intentionally to see how much you're paying attention. Probability of horse number 2 is actually 1 out of 36, right? 1 out of 36. So if I want to know how often in 1,000 races horse number 2 or horse number 12 is going to win, because it's the same probability, what do we get here? 1/36 times 1,000. I'll repeat that. 1/36 times 1,000, because you all had enough time to work on this. You even had enough time to discuss. You just chose not to. Thank you, Cambria. Good. 27.7 repeating. We definitely don't want to discount that 0.7 repeating, so we would say that's about 28 times. And it would be the same for horse number 12. Suppose we watch the horses race 500 times. Which of the following values would be the most likely result for horse number 5? So we saw the horse races 500 times. We want to know how often we probably saw number 5 win. Are any of these going to be perfect options? No. Which one is going to be the best? Explain your reasoning here. Alexis, how'd you get 50? Why is that your choice? Great. Where did this 4 over 36 come from? Great. That's the theoretical probability for horse number 5. So using the theoretical probability, we multiply it by the number of races that we have. And tell me what you got. You got 55, you said? 55.5 repeating. Now, again, this is an example of our theoretical probability tells us it probably should happen about 56 times, 55, 56 times. Is that one of our options? No. So which one is the best one? This experimental probability is probably the closest option. Way closer than 11 or 100 or 250 wins. Last one, and this is where our probability models are really going to be helpful here. How do you think individual probabilities relate to the probabilities of the sums? For example, the probability of rolling a 1 on the first die and a 6 on the second die is 1 out of 36. We can see that in our probability model. A 1 in the first die, where is it here? A 1 in the first die and a 6 in the second die. That happens just one time, 1 out of all 36. So how does that individual probability relate to rolling a 7? The probability of a 7 is 1/6. Why? Why is that happening? Those probability models will be helpful, but I want you to discuss with your group so that we can have a really good productive discussion on the video. Ready, set, go. Why? Why is this happening? Good. We'll start with Gideon. Good. This is only one of 6 options to roll a 7. Continue. Yeah, fantastic. Great job. Zuri, did you have any other comments you'd like to add to that? Okay. Yeah, so again, rolling a 7 can happen in a whole bunch of different ways. When we go back to that probability model, we can see we can roll a 7 1, 2, 3, 4, 5, 6 different ways. But there is only one way that we can roll a 1 first and then a 6 on the second die. That only happens one way. A great summary. Your homework is the 1.1b homework section. So it's only just a couple of problems. That's it. Thanks for watching, and we'll see you next time.